This clip contains a tricky science problem. Squeaky shoes. More specifically, the squeaks that happen when a soft surface quickly slides over a hard one. An everyday occurrence.
But when you dig deeper, we cannot really often explain them in a very satisfactory way.
Soft and rigid bodies, when they're sliding against each other, behave in a completely different way, especially when we're sliding at fast speed. I was expecting something quite boring, to be honest, and it turns out that it's a combination of earthquakes and lightning.
It's not just shoes that squeak when soft soles hit hard flooring.
For sure, your bicycle brakes that are rubber pads onto metal, they're very much the same problem. Some biomedical implants that involve joints, they tend to squeak too.
If you take a hand or a finger and you slide it against a smooth surface, dry, the type of sound that you hear, if you slide it fast, and you can do the experiment now if you want, this is squeaking as well.
With these squeaks being so common, you'd imagine they'd be well understood. But actually,
we knew very little, okay? So we had an initial hypothesis that something called Shalamach waves, these are wrinkles, the same as when you run your finger on your skin, you see these wrinkles, and these wrinkles slide under your finger, right? But these Shalamach waves, they're super slow. The rate at which you can produce them is too low in comparison with the sound that you hear. So, okay, we had this, maybe they were involved, maybe their rate of generation somehow changes, but we discovered something completely new.
They looked at rubber blocks that had patterns on them similar to what you'd find on the bottom of your shoes. To understand the true cause of the squeaks, the team needed to look at the frictional interface, the point of contact between the two surfaces, as the soft and hard material slid over each other quickly.
So people for a long time have looked at like rubber glass interface and took images of those interface, but basically all the study have been looking at very, very small velocity of sliding. The main thing that we did different, but like crucially, was to slide fast enough to have squeaking and measure at a very high frame rate.
And so we designed this very simple system inspired from Da Vinci from the 15th century. Basically, it's a weight that you drop and that slides an object. And so now we have this controlled normal force that we can apply, and we put LEDs everywhere in this acrylic plate that we attach to powerlifting weights, and then we have this high-speed camera that could image a stationary object as the interface was sliding.
Recording this super fast footage of hard acrylic sliding across rubber blocks allowed the team to make several new observations.
At the interface, we see some local stick-slip dynamics. So what does it mean? It means that like at the point of the interface lifts, so physically open and detaches, and then this region that is open and detached travels very quickly at the speed of sound of the rubber itself.
Think about it as a rug, and you take this rug and you do this, okay? So you have a pulse that is traveling. This is exactly what happens at the interface, right? And it's happening at the speed of sound or even faster than that.
By measuring the repetition rate of these opening pulses using their high-speed video, the team were able to show that the rate of the pulses matched the frequency or pitch of the audible squeak they had recorded at the same time. But they also found that this wasn't the case if they removed the pattern of ridges from their rubber blocks.
The main discovery is that geometry matters. Small details matter in friction. And specifically in this case, when you take a flat rubber and you slide it, you'll hear a sound that is akin to taking a tape and open it. Okay? And the moment you put these fine details, very, very tiny details, at the interface, all of a sudden you hear a musical note. A note. So main frequency and its harmonics. Most of people thought of slip pulses of this magnitude and speed in the geoscience field. So think about earthquakes, for example.
Without a pattern, the opening pulses travel in multiple directions and trigger a variety of vibrations in the block, making a noise, but not a clear squeak. The ridges channel the pulses and so the block's vibrations into a single frequency or pitch. That's what happens with the grip on the soles of squeaky shoes too. And that wasn't the only surprising finding. The researchers saw that the pressure applied to squeeze the two surfaces together didn't change the pitch of the squeak, but applying more pressure did affect how the opening pulses got started.
If you slide it, and if you slide this rubber and you put it under a sufficiently high pressure, tribocharge happens. So, just like rubbing a balloon on your head, that gives you this electrostatic charging. And what happens is that it discharges. And when it discharges, it creates a mini explosion or a micro explosion in the contact area. And that's enough to create pockets of high pressure that nucleate an opening slip pulse.
Further investigation showed the pitch of these lightning-initiated squeaks is defined by the height of the rubber block. Understanding this gave the team an idea for a demonstration.
Well, we're talking about squeaking. Squeaking is a noise. It's a note. What do you do with notes? You can speak, as we're doing now. You can also make music.
It's an excellent showcase of also the robustness of our finding, because when you play these blocks by hand, sliding them on top of a glass plate, you cannot control the small torques and angles in the same precise ways that we do in the experiment, but they can have a very reproducible sound.
Even if these squeaking rubber blocks don't catch on as a new instrument, Adele and Gabriele think this work could have an impact in a variety of fields, be that earthquakes, metamaterials, or engineering.
And then the natural question that arises is like, how can we then design and optimize intricate shapes of those contact ridges and patterns so that we can better control the sound, suppress the sound, control the friction resistance, and so on.